Fraser got a problem with me. He's right there. I don't know where it is.
Well, this is awkward. What do you you want some time to think about it?
Okay, who do you really want to go with? I really appreciate your offer, Peter. It's not that I'm saying no. I'm not saying no. I just have to see what my options are. I need to see what my options are, Peter. We're done.
All right. Okay, guys.
It's like a soap opera.
Okay, so. Oh, is it going? What's happening? All right, it's recording. All right, so here we go. All right, so honestly, in terms of problem solving, this section is the same as what we did yesterday with the peanuts and pigs. Okay, so yay because it's the same. Boo because it's the same. The only difference here is we're gonna be pulling objects instead of pushing. All right. So you guys, I want you to think of tension force. So a couple things you need to be aware of on tension force. First of all, at this point in the year, the tension force at both ends of our rope will always be the same. Okay. So if you look at this example here, this is the force of the hand pulling the rope, right? The reaction is the rope pulls the hand. Yes. Those two forces are equal, right? So it turns out that the tension at the other end of the rope is the same. Okay? So the force of the rope pulling the box is the same as the force of the box pulling the rope. Okay? So I guess what I was about to say is this. I kind of like to think of the tension force, or the rope itself, I guess, as, and this is sloppy, but it kind of helps me process what's going on. Think of the rope as a conduit for force. All right? The rope allows this hand here to pull the block without physically touching it. Okay? In other words, if the hand is pulling the rope with 100 newtons, for all intents and purposes, that's the exact same as the hand pulling the block with 100 newtons. Cool? All right? And so there's an action-reaction here, right? If the hand pulls the block with 100 newtons, then the block pulls the hand with 100 newtons, and the rope sort of communicates that force from the block to the hand. Follow? Okay? But the forces are equal at both ends. Okay? Make sense? For any one given rope, the tension will be equal at both ends. Okay? All three of these drawings, assume that the force of the hand is the same. All three of these drawings are going to result in the same tension. Okay? Because if the hand is pulling the rope with 100 newtons here, then that's the tension in the rope. Same here. If the hand pulls the rope down with 100 newtons, that's the tension in the rope. Same over here in this last drawing. So all three of those drawings are going to represent the same tension, assuming that the force of the hand pulling the rope is the same.
And that's why I can't just...
Sorry?
No, I just right under it.
Gotcha. Okay.
But then I
Oh,
realize it's on different.
yeah. So, yeah, maybe we should talk about this, I guess. Yeah. So, we're never going to talk about the net force on the rope. Well, I guess I shouldn't exactly say that. It's sloppy to talk about the net force on the rope. Because net force is mass times acceleration, right? But what are we assuming the mass of our rope is? Zero, right? Okay, we're always assuming that the mass of the rope is negligible, okay? And so for that reason, we usually won't talk about the net force on the rope, okay? Which is why it was a little sloppy that we did that with that track flight problem. Okay, so I guess the other thing that you need to be aware of is basically all a pulley does is it sort of bends the force, or it changes the direction of the force. Okay? In this example, the force of the hand and the force of the tension are the same, right? As far as the box is concerned, right? Okay? But over here, the force of the hand is down, and the force on the box is to the right. Make sense? So the pulley is basically accomplishing the task of changing the direction of the force. All right? So when this happens, you guys, this system here can basically move one of two directions. The system is either going to go this way, or I suppose it's possible that somehow the box could move this way. I don't know how that could happen, but maybe somebody's over here pulling the other way. Okay? So when you do that, you sort of need to come up with your own conventions then for positive and negative. Okay? I will usually choose the direction of motion to be positive. All right? So if we assume in this example that the whole system is going to move this way, then I'm going to make this a positive direction and this a negative direction. Make sense? Okay? And so it's still linear motion, except that our line is sort of bent because of the pulling. Follow? It's linear, but it's curved. Okay? Are we good or no? All right. Pretty loud. All right. And then same thing over here, right? So if we assume that the hand is pulling the rope, then I'm probably going to make this way positive and this way negative. Follow? All right. So I think probably the easiest way is to just dive right in and do an example or two. All right? So let's do this. So in this image, the boxes have the given masses. So this one has a mass of 3m, this one has a mass of m, and this one has a mass of 2m. No numbers. All right, so based on that, oh, we're also told the applied force over here has a magnitude of 12 times mg. That's not 12 milligrams. That's 12 times m times the acceleration of gravity. In other words, 12 times the weight of m. Good? All right, floor is frictionless. So in terms of m and g, we're trying to find the tension T in that middle rope. Okay, so technically here there are 4 free body diagrams, right? So I'm going to really quickly plow through those free body diagrams. I'm going to, what forces can I safely ignore for this whole example? Gravity and normal force, right? Because they're always going to cancel, there's no friction, right? Okay, so let's make 3 free body diagrams. So, A and B and C combined. What forces act on them? Just the force. Okay, so that's one free body diagram. Good? I guess we can do a thing now. What can we do now? Bless you. Can we do anything here, you guys? Are there any other forces on my system that I care about? There's gravity and normal force, so let's cancel out. So, oh, well, I know my net force. So let's find the acceleration of the system. Right? It's net force over mass. So let's see. My net force is 12 mg. What's the mass? Is it m?
6m.
6m, right? 3m plus m plus 2m gives us 6m. So you get 2g. Aha! So there we go. There's the acceleration of the system. Right? Because that one force is moving all 3 boxes. Good? All right. So, now we're trying to find the tension T. So, to do that, I guess we could just directly look at, let's look at, well, you guys tell me. What box should I look at next?
A. Not A.
So it doesn't really matter. I think the most direct way to do it is to look at C. Because how many forces are going to affect the motion of C? 2. Do we know what either of those forces?
Yes.
We do. We know one of them. We got to find the missing one, right? So let's try it. All right, so let's look at box C. So here's box C. I know that there's a force of 12 mg pulling it forward. And there's the mysterious, I don't know why I'm saying mysterious, tension force T pulling it backwards, right? I know one other very important thing about box C. That's okay. It has a mass of 2m. And I know something else too. We know the acceleration is 2g, right? Follow? So what should I do? Oh yeah, I guess net force equals net force. That works. I wasn't thinking of it that way, but that works. Actually better than what I was thinking. So let's go with that. So let's see. Net force equals net force So this is mass times acceleration equals F plus T, right? So let's see, my mass is 2m. My acceleration is 2g. F is 12 mg plus T. So you get negative 8 mg.
What were you thinking, Mr.
No, I was just going to do it in a couple steps. Good, you guys? All right, and then you could go through a similar process and make free body diagrams for boxes A and B. Good? Do I need to do that, or is that, you guys kind of see where we're going here? Okay, cool. All right, so that's that example. Everybody happy? Cool. Questions before we go on? Yeah?
Why isn't T negative? Like, because like that.
Yeah, I guess you could have put minus T here and just then assume tension is a positive value.
Okay.
And then that makes this positive. That's fine. That's sort of a tomato-tomato
Either way,
thing.
it's fine.
Yeah. Yeah. So to your point, you guys generally, in general, when somebody says, hey, what's the tension in that rope? They'll usually give you a positive value. Because if you think about it, the tension in the rope is exerted in both directions. So necessarily one end's going to have to be positive and one's going to have to be negative, right? So you just understand that and you just say the tension is 8 mg or whatever it is. So to be honest, I like your answer a little better. All right. Are we good? Okay, let's try another one. What do we got here? All right. This one is the same idea except there's friction. The process is very similar. The only difference is we've now got more sort of external forces, right? Because the friction comes from whatever the table or surface is, and that's, no matter what we choose as our system, that's going to be an external force, right? Well, I guess we could choose the ground as part of our system, but then it gets ugly. So, let's run through this. Oh, okay. Oh, good, because we don't have to do pulleys yet. That was what I was worried about. I was worried. Okay. All right, so I think we have just enough time to get through this example. If I can find my notes that I have written down over here. Okay, so it says in the image below, so same setup. So the boxes have a mass of 3m, m, and 2m. Our force is 12 mg. All right. So at some point, we're going to need to find the forces of friction affecting each of the boxes. All right, there are two ways to do this. You can find the three forces individually, right, just by doing normal force times coefficient of friction. Follow? So normal force times coefficient, normal force times coefficient, normal force times coefficient. So that's one way to do it, and it works. And to be honest, it's probably the safest way to do it. Okay. It turns out, though, that because the coefficients of friction for each of the three boxes is the same, you can take a shortcut and treat all three boxes as one box. Yes. Does that make sense? Mm-hmm. So that's cool if you're looking at the system, but eventually you're going to have to break it up and find it for each of the individual boxes anyway. Okay, so I think I'm going to take a quick second and do that. All right, so let's look at each of the three boxes and identify force of gravity, normal force, and maximum friction, maximum static, and kinetic. All right, so here we go. So block A, when you do that, here's what you discover. Your force of gravity is 3 mg. Your normal force is 3 mg. Your force of friction static max, if you figure it out just by doing normal force times coefficient, it gives you 1.2 mg. And if you find your force of kinetic friction, it gives you 0.9 mg. Does everybody see what I did there or no?
Yes.
Any problems? Okay, so I'm going to really quickly do the same thing for B. That's everybody cool with this? Am I going too fast? Good. Sarah, you doing okay back there?
Oh, yeah, thanks.
Sarah, are you good? I'm always worried about you being able to see because you're always. You and I need to go like get our eyes checked together. All right. So let's see. Block B has got a mass of m, so we got mg. We got a normal force of mg. Your force of friction static max is going to be 0.4 mg, and your force of friction kinetic is 0.3 mg. Over here is block C. It's got a force of gravity of 2 mg, a normal force of 2 mg. Force of friction static max turns out to be 0.8 mg and 0.6 mg. All right, so a lot of information there. Any problems? Okay, so what do you want to do? We got to find the acceleration of the whole system and the tension again. What are you going to do?
Acceleration.
Sorry?
Plug it in for acceleration.
Plug what in for acceleration?
Use that force.
Net force equals net force for which system? A, B, C, combined, A and B, B and C, A and C. The whole thing? Sabo, what are you thinking?
Does it matter?
It does. So let's finish our free body diagram. So for C, we've got a force of 12 mg pulling it forwards, right? Tension is pulling it backwards. I don't know how much tension there is. That tension is going to determine whether or not box C moves, right? Because if the tension makes my net force less than 0.8, then it's not going to move, right? So I don't know this tension, which means I don't know which kind of friction to put in, so I've got two unknown forces in this drawing. Follow? All right, let's see. Let's look at box B. We've got that same tension force pulling it backwards, and then we need to give this a name. Let's call this T2. Is that cool? We got T2 pulling it backwards. So now on this one, we've got two unknown forces and friction. So box B, we're totally hosed. Box A has got T2 pulling it backwards and then some sort of friction, but we don't know what kind of friction. So, what should I choose as my system?
C. I thought it was
I thought we already ruled out C.
A. Oh, wait.
The entire thing.
We got to do the whole thing.
Oh.
Okay? So, looking at the whole thing as my system, here's A plus B plus C. We've got a force of 12 mg pulling it forwards. All right? Now, what's going to try to stop it? Friction. What kind? Static. So we've got three external static friction forces, right? One on A, one on B, one on C. If I combine them up, let's combine them up. That's terrible English. If I combine them up, then you get 1.2 mg plus 0.4 plus 0.8. Is that going to give us enough to prevent the motion?
No.
No. Okay? So, that 2.4 mg over there is not enough to prevent my system from moving, so I'm going to have kinetic friction, which is negative 1.8 mg, and from there you can find your acceleration of the system, and then go back and fill in the other information for A, B, and C. Sarah?
How do you know it's not enough?
So remember, static friction has a maximum amount of force that it can exert, right? So we've got these three different maximum static friction forces, right? We got 1.2 from box A, 0.4 from box B, and 0.8 from box C. Okay, if you add all of those up, that gives you a total static friction force maximum of 2.4 mg. You good up to there? Everybody good up to there? All right. Now, how much force is trying to move it? Oh, 12 mg. This 12 mg is more force than static friction has. So if this had been just 2 mg, then static friction could have prevented the motion, right? Let me say it a different way. If static friction prevents the motion, you guys, what's the net force going to be? 0. So can static friction make the net force 0? No, because it would need 12 mg and it only has 2.4 mg. Follow?
Yep.
Yeah, Christine? Shh, guys, quiet please. I know the bell's about to ring, but...
So you're saying the tension forces are different between boxes?
Yes.
Oh, no.
Because this first rope has to pull... Oh, here's a good question, you guys. And this comes up in one of the homework assignments. Without doing the calculations, which of the three forces... Better yet, rank the forces from biggest to smallest. F, T, T2. Real quick, before you go. Which force has to be the biggest? F. Why? It's moving the most mass. What's the next biggest? T, and then T2, right? Okay? So, 4-1 due tomorrow, or 5-1 due tomorrow, rather.
So do I keep my tests and see what I get
Yep,
grades?
keep your tests. Learn.
So I can-
Yes.
will my grades